Good evening, everyone. Welcome back to AISC's Night School. This is Bracing Connections and Related Topics, presented by William A. Thornton. Today is October 20th, 2014, and this is Session 4, Vertical Bracing Connections, Corner Connection Part 1, addressing wind and low seismic systems. My name is Brent Liu. I am with AISC, and I will be moderating today's presentation. I want to welcome back our speaker, Bill Thornton. Dr. Thornton is a corporate consultant to Surveys Corporation of Roswell, Georgia. He is the winner of the AISC 1995 T.R. Higgins Lectureship Award, as well as the 2003 AISC Lifetime Achievement Award. He has served as an invited lecturer numerous times for AISC as well as for various state structural engineering associations. He is the author or co-author of many published papers in connection design and other structural areas. He serves on various committees for ASCE, AWS, RCSC, as well as AISC. He was also the chairman of the AISC Committee on Manuals for more than 20 years. Most recently, Dr. Thornton was recognized for his achievements and contributions to our industry. In 2013, he was inducted into the National Academy of Engineering. Very pleased to have you back here this evening, Dr. Thornton. I'll hand things over to you.
Thank you, Brent. And good evening or good afternoon, ladies and gentlemen. Good to be back. Tonight's subject is the first detailed connection design problem. Some of you have been wondering, I think, if we're ever going to get into actual calculations. I think we'll get into those in spades tonight. This is part one. Next week we'll be doing a high seismic design. Tonight it's low seismic, wind, just sort of ordinary design. So this is just the title, Bracing Connections and Related Topics. That's the title of the webinar. We're item 4 here, Vertical Bracing Connections, Corner Connections, Part 4. and tonight we'll do a vertical bracing connection in detail. We'll begin with the brace to gusset design. This will determine the gusset dimensions based on the brace to gusset connection. Then we'll check the gusset to column connection, then the gusset to beam connection, and then the beam to column connection. So every one of these connections has got 4 separate connections that you need to deal with. Brace to gusset, this connection, say gusset to column, gusset to beam, and beam to column. Many of the limit states associated with these 4 connections are repeated. All of the limit states will be considered in this presentation, at least in the handout that you have, but we will not go through them all in detail because it's just not enough time in an hour and a half to really get through every one of them. And you'll see the way we'll handle that as we go on. This example you've seen before. I don't know whether it was the last session or the session before. We used it to do some calculations of the forces for the uniform force method. But this is the basic information. It's AISC, 14th edition manual and specification. The example will be done in ASD terms. Next week we'll be doing an LRFD. The beam to column and gusset to column connection have 4 rows of bolts. That's the N equals 4. The weld length is prescribed. That's the horizontal weld length between the gusset and the beam, to be 20 inches with a 1/4 inch min. The bolts are A325N, threads excluded, standard holes, 3/4 inch diameter, standard holes unless noted otherwise. The angles, double angles, 4x4x3/8, grade 36, with horizontal short slots in the outstanding legs. And the edge distance, L sub EV, on the angles is 1 1/4 inches. And the bolt spacing is 3. The brace force is specified as plus or minus 75 kips. The slope is 43.8 degrees. The angle from the vertical used for the uniform force method is 46.4. The gusset is a 3/8 A325 plate, and the WT and W shapes, the column and the beam, are all ASTM A992 grade 50. So let's continue. Each part of the connection that we deal with will be highlighted in yellow, as you see here. We'll begin the example by designing the brace to gusset connection. This will help to set the geometry of the gusset. Determine the number of bolts required to attach the brace to the gusset. Check gross and net tension and block shear for the brace. Check bolt bearing and tear out of the brace and gusset. Check block shear and Whitmore tension and buckling for the gusset. So, starting off with bolt shear, just to get an idea of where we are. The bolts are A325, a 3/4 diameter. They have a single shear value, ASD, of 11.9, as you can see here in Table 7-1. We have 8 of them. So 8 times 11.4 gives me 95.2 kips, greater than 75 kips. So we're okay. Probably the connection will look pretty much like what we see here. It might change a little bit in some cases, but it won't tonight. I mean, if tear out or something like that, or block shear was an issue, you might have to space the bolts out more than at the 3-inch spacing that we've specified for this particular problem. Brace to gusset. One of the first things that's usually checked is the gross tension of the WT 6x22.5. This really isn't the connection designer's responsibility, maybe, but I think it is, because if the brace is no good, then everything else we're doing is we're just spinning our wheels. So let's check the WT gross tension, which is the tension area. The gross area is 6.56 inches squared. The yield strength is 50. The safety factor is 1.67, gives me 196 kips, greater than 75. Okay. The next check would be net tension. Sometimes engineers pick these members without paying attention to how they're going to be connected. You're going to have some holes in this thing, which is going to reduce the tensile strength, and also there are shear lag effects, because not all of the elements of this WT will be connected. The stem will be sticking up in the air with no connection to it. The width of the holes is taken as a 1/16 greater than the nominal dimension for these net tension calculations. The shear lag factor is from table D 3.1. This is table D 3.1. We're looking at case 2 here. It says all tension members except plates and HSS, et cetera, where the load is transmitted to some but not all of the cross sections. And it's just blowing that up. The formula that we have for this is shear lag factor equals 1 minus x bar over L. What are those terms? Well, x bar is the distance from the faying surface. The faying surface for our connection is right here, to the gravity axis of the brace. This particular slide says if you have a wide flange that's connected to the flanges and not the web, then x bar would be the gravity axis position of a WT that's cut from that wide flange, which is exactly what we have here. So we can look this number up, x bar, in the tables in part 1 of the manual, and you'll find that x bar is 1.13. The length of the connection out to out of the bolts is 9 inches. So therefore U is 1 minus x bar over L. 1 minus 1.13 inches over 9 inches gives me 0.874. To simplify the calculations, instead of repeating a whole diameter plus a 1/16 all over the place, in a lot of the calcs, what you'll see is the 13/16 plus a 1/16 gives me 7/8. The section that we're looking at is shown here by the red line. We're looking at what happens right along this section of my WT where the holes are. So the net the effective net area, A sub E as it's called, is the shear lag factor times the net area. The net area is the quantity in the square brackets, which is the gross area minus the area of the holes. So the thickness of the flange of the WT is 0.575. There are two holes. The size of the bolt, the size of the hole is 7/8. So subtracting out that from the gross area gives me an effective net area using the U factor of 4.85. So the tensile strength, F sub U times A sub E, the rupture strength or the fracture strength, 65 times the effective net area divided by the safety factor of 2 gives me 158, greater than 75. Okay. The next set of slides has got to do with block shear. This picture shows you a pretty graphic block shear failure. There's two failure surfaces for block shear. You've got this net tension area right here between the bolts and tension, and you've got a shear area shown in this slide, which is the area along the bolts. There are two of them, one up here and one down here. The formula for all this from spec section J 4.3 is written as you see it here. R sub n, the nominal strength, is the shear rupture strength times the net shear area plus the UBS factor, which we'll talk about in a minute, times the tensile rupture or fracture strength, or the shear yielding strength, 0.6 F sub y times A times G sub V, plus again the net tension fracture strength. These terms, that term and that term, are exactly the same. The UBS factor is a factor that you can find in the spec. Basically, it's 1 for everything we'll be doing here tonight. The commentary and the spec says it's 0.5 if you had, say, a double column of bolts that's like a clip angle with two columns of bolts. Something like that, it would be 0.5, but it'll be 1 for everything that we're doing. So let's calculate the properties to calculate bolt shear. This slide calculates the effective lengths, L sub GV. That's the gross shear length. It's 10.5 inches. It's this length right here, from the end of the T to the most inboard hole. It's 1.5 inches edge distance plus 3 times 3 is 9, gives me 10.5. Then for the net shear, we take basically the gross shear, which is the first part of this, and we subtract out the holes. So we have 3.5 holes times 7/8 of an inch for the width of each hole. Gives me 7.44 inches for the net shear length. And for the tension part of it, the length for net tension is basically the width of the flange of the T minus the gauge over 2, and then taking up one hole, half of a hole out. Basically what is being calculated here is this little bit right here. Of course, there are two of them, but right now we've got this one, and we've got all the lengths for just one of these two. So to get the areas, we multiply the lengths by the thickness of the flange, and we multiply them all by 2 because there are two block shear pieces that can tear out. Gives me these numbers: gross shear area 12.08, net shear area 8.56, net tension area of 0.96 inches squared. So substituting all that into the formula for the nominal strength, this first term here is the shear fracture strength, 0.6 times 65 times 8.56. That's the shear, the net shear area. Gives me 334 333.8, and then this term here is the gross shear yield strength, 0.6 times 50 times the gross shear area, and it's 362 kips. So what counts is the smaller of these two, 333, you see it here, and this second term, this one down here, which is common to both of them, 65 times the net tension area, gives me 62.4. So add those together, gives me 396. Multiply that by the factor of safety of 1/2. Multiply it, divided by the safety factor, gives me 198 kips greater than 75. Brace to gusset block shear. Now we would do exactly the same thing, except we will be doing it for the gusset rather than the WT. You have to do both. The formulas are exactly the same. All the calculations are given here, but the lecture will skip to slide 35. The reason we're skipping that is we don't have time to go through it all again, and there's nothing new. And all of the calcs that are done that we just skipped, you can look at yourself and see that they're exactly the same as what we already did for block shear for the WT. I mean, the failure mode is a little bit different, but it's basically the same idea. The next thing that I want to talk about is bolt tear out and bolt bearing. And these, although they're listed in the specification as bearing, they're really quite different limit states. And I believe that in the next edition of the specification, they will be broken out to be tear out and bearing as separate entities. You can see for tear out, you kind of get some sort of a rupture or fracture taking place, whereas for bearing, you get kind of a mud wave in front of the bolt. You get a lot of yielding. Here you're getting something that's going to ultimately fracture. It's going to pull a piece out. The next slide shows you tear out and the limit state that we use for it. Basically, we assume that it's going to fail along these broken lines that you see here. If I could control this arrow, I'd be all right. There's two broken lines. The length of those lines to the face of the hole is L sub C. That's the clear distance from the face of the hole to the edge of the plate. If we had another hole in here, L sub C would be the clear distance between holes. There are two shear planes, and the shear limit state, the shear fracture limit state, is 0.6 times F sub U times L sub C times T. That's the shear strength of one of these two, and then there's two of them. So that's where the 1.2 comes from. 1.2 times F sub U times L sub C times T. So, continuing. In reality, the tests that were done to establish this formula, some of the tests failed like you see here, but the formula in the specification, in the manual it says here, but it's actually in the specification itself, is pretty accurately predicted by the 1.2 formula. So, we already checked bolt shear, 11.9 kips per bolt. We had 8 bolts, and we came up with about 95.2 kips capacity. But that might not be the right number, because bolt shear is only one of 5 limit states that need to be checked for each bolt. And those limit states are bolt shear, which we already checked, then bolt bearing on the main material, bolt bearing on the connection material, bolt tear out on the main material, and bolt tear out on the connection material. And then for each bolt, the smallest of these 5 for each bolt is added up to get the capacity of the connection, the design strength of the connection. So let's look at how this works. For bolt shear, we've already done that. We know that for bolt shear, it's 11.9 kips per bolt. So let's look at bolt bearing. This is for the main material, for the WT. It's 2.4 times the diameter of the bolt times the thickness of the flange times F sub U. 65 divided by the safety factor 2 gives me 33.6. Then bolt tear out for an edge. The edge is this one right here. This is L sub C, the clear distance from the center of a hole, from the edge of the hole to the edge of the plate. So it's 1.5, that's the edge distance, minus half of a hole diameter. And for this calculation, we don't use the hole diameter plus a 16th. The actual physical tests were done with, and the theory was presented with the hole diameter, so it's 13/16. The thickness of the flange, well, wait a minute, the thickness of the flange is 0.575, and the tensile strength of the flange is 65. The safety factor is 2. That's 1/2. Divide by 2, it's 1.2, gives me 24.5 kips. Then to tear out of the center bolts. The center bolts would be one of these in here. The clear distance there is the spacing. Divided by, subtract one hole. Thickness of the flange, tensile strength, 1.2, factor of safety gives me 49.1. Continuing, for plate bearing, this is bearing on the plate. 1.2 times the diameter of the bolt times the thickness of the gusset times 58, which is the tensile strength of the gusset, divided by the factor of safety, 2, gives me 19.6. Then plate bolt tear out for an edge bolt. That's this one down here. We have, again, 1.5 minus half a hole, 13/16 over 2. And then we'd have the thickness of the gusset. We'd have 58, the tensile strength of the gusset. Safety factor, 1.2 gives me 14.3. Now, none of these yet have gotten down to 11.9, so we're still okay. Continuing, plate tear out. This is the gusset plate. So the center bolts, like in here somewhere. Here somewhere, we would have 3 minus 1 hole, gives me 28.6, and then we have, for the top bolt, for each bolt we would now summarize the 5 values that we have for the top bolt. We've got all these bearings and tear outs. We've got bearing on the main material, tear out on the main material, bearing on the connection material, tear out on the connection material, and bolt shear. Well, it turns out, in this case, it's 11.9, which is where we started. And then for each of the other bolts, this is for the center bolts, calculating, taking the minimum of the 5 values for the center bolts. Again, the least is going to be 11.9. And then for the bottom bolt, taking the least of all these values, again, it's 11.9. And so you would end up, of course, with where we started. 11.9 is the value, but it might not be that way. So you'd have the design strength of the top bolt, the design strength of the center bolt, and there's 2 of those, and the design strength of the bottom bolt, and then there's 2 lines of bolts. This was all done per line of bolts, so it's 11.9. 11.9 times 2, 11.9 again. Add those up, multiply by 2, you get 95.2. Greater than 75, that's where we started from. But you have to keep in mind, if this gusset was, say, 1/4 inch thick, it's very likely that one of these bolts in here would have a value less than 11.9. You need to look at 5 limit states for each bolt. I know it's a pain, but that's the way it is. You've got bolt bearing for the main and the connection. You've got bolt tear outs for the main and the connection, and for tear out, you've got different values depending upon center bolts or edge bolts, and then you got bolt shear. And the least value of those 5 for each bolt, added up to get the capacity of the connection. This particular example doesn't demonstrate that, but that's what you have to do in general. The next set of slides has got to do with the Whitmore section. The Whitmore section was first introduced in the bolt guide, which the bolt that I mentioned, I think 2 sessions back, by Kulak, Fisher, and Struick, first published in 1974. The Whitmore section was actually developed at the University of Tennessee in 1952. It wasn't used, as far as I know, at all until the bolt guide book came out in '74, and its second edition in '87. Anyway, what Whitmore came up with was that from the beginning of a connection to the end of a connection, if you spread the load at 30 degrees each side, you get pretty darn close to calculating what the stress is on a section of your plate. This one went to the limit, it fractured, but you can see that it's pretty darn close to being 30 degrees each way. For our connection, we're still in the brace to gusset. This shows the Whitmore, the angle between this red line here and the angle of the brace itself is 30 degrees. The Whitmore section is this length from this point to this point. Whitmore compression will always control over tension. I mean, they may be equal, but if the unbraced length is big enough, then compression will control. Unbraced length is the buckling length. This dimension right here, it's 8.81 inches. The length of the Whitmore is the gauge, which is 5.5 times the tangent 30 times 9. 9 is the distance out to out of the bolt. And there's two of those, gives me 15.9 inches for the Whitmore section, the length of the Whitmore section. Sometimes the Whitmore section will go into the beam. In this case, it does not. There's a general discussion of the Whitmore section in modern steel construction, written by Carlo Lini of AISC and myself, published I think in about 2012, which gives you all of the kind of details that you need to consider it in general. So, in this particular case, the length of the Whitmore is in the gusset, it's 15.9. The buckling factor, the K factor, is 0.5 from tests that were done by John Gross at NIST. It's the value that's used in all the AISC's design examples in volume 14.1. This is available at www.aisc.org. Example 2.c, Roman 2.c-2. Anyway, unbraced length, K times the unbraced length times the radius of gyration, which is the thickness of a plate over the square root of 12, gives me 40.7. That is the slenderness ratio. We can calculate the critical stress from table 422 pretty easily for A36 plate. For KL over R of 41, which is just the next figure, it's 19.7. That's the value that we use in this example. You can calculate this from Part E of the specification. You get exactly the same number. This kind of explains a little bit more here. The effective length factor was established as 0.5 by full-scale tests done by John Gross in 1990, published in AISC, Engineering Journal. The gusset plate is supported on both edges, it's assumed in this particular case. More recently, Bo Dowswell in 2006 wrote a paper, again, AISC Engineering Journal, effective length factors for gusset plate buckling. For this type of a gusset plate, I believe that Bo's work would indicate that buckling is not an issue. It's really a pretty compact gusset, but we're still using 0.5 here because the AISC spec doesn't exactly include Bo's work, and we want to make sure that we satisfy the spec. Anyway, the critical stress over omega, F critical over omega was 19.7. Multiply that by the thickness of the gusset and the length of the Whitmore section. That's the buckling area. Gives me 83 kips, greater than 75 kips. Okay, but we're getting close, aren't we? You could also check Whitmore tension, but for Whitmore tension, this 19.7 will be about, 21.6. So it's not going to control. I don't think it ever controls, but if you have a connection where the KL over R is less than 25, basically you would just be checking yield anyway. All right, the next part of this presentation is to calculate the forces that act on the gusset interfaces, which are shown here in red. I think that's red anyway. Gusset to beam, gusset to column. We'll use the uniform force method to do this. We've already done this in an earlier presentation. Here are the formulas to remind you what they look like. Probably the one that you have to keep in mind mostly is this one in the box called the constraint, which the ideal values of alpha and beta must satisfy. What are alpha and beta? Alpha is the distance from the face of the column flange to the ideal centroid of the gusset to column connection. Ideal in the sense that if we put the centroid of the connection right there, we'll have no couple on this edge. Beta is the counterpart for the gusset to column connection. Beta is the distance from the top flange of the beam in this case. Could be the bottom flange if it was a bottom. Gusset to the centroid of the ideal position of the centroid of the gusset to column connection. Ideal in the sense that if we satisfy this constraint with alpha and beta, there are no couples here either. There are no couples here at the gusset to beam connection, and there are no couples here at the beam to column connection. So you have pure uniform forces on every interface. So continuing with the UFM, the tangent of the angle theta from the vertical is the tangent of 46.4, if you remember. That's 1.05. E sub B is half the depth of the beam, which is 8.2. E sub C is half the depth of the column, 6.05. Note that E sub C would be 0 in connections into a column web, except for special case 4, which was introduced a couple of sessions ago. So let's continue with it. Beta bar, what's the difference between beta and beta bar? There have been some questions about this sort of thing. Beta bar is the actual distance to the centroid of the gusset to column connection. From the geometric layout, the horizontal dimension, actually it's the vertical dimension of the gusset, is 16 7/8 inches. That's this distance right here, from here to there. And we will place the gusset to column connection right dead center on that. So we'll pick beta is 8.5 inches. Beta bar is 8.5 inches. That's the centroid of the connection of the gusset to the column. Let's also pick beta, the ideal location, to be exactly beta bar. Then, using the constraint, we can calculate the ideal position for alpha. And that turns out to be, from the geometry here, 11.5 inches. Now, we already established that we were going to use a weld length here of 20 inches. So that means that alpha bar, the actual centroid of the gusset to beam connection, will be 20/2 plus the setback of a 1/2 inch, which is 10.5. It doesn't equal alpha. We will leave it this way for illustrative purposes, but there's absolutely no reason, as I've said early on, that I couldn't make alpha bar equal to alpha simply by making this 20 inches here 22 inches. So if I had 22/2 is 11, plus a 1/2 would give me 11.5, which is exactly the ideal value of alpha. But for illustrative purposes, because it's interesting to see what happens and to actually do one, it's being kept at alpha bar is 10.5 and alpha is 11.5. Now, when you calculate this geometric parameter, which was defined in an earlier session, the alpha and the beta in here must be the ideal values. It turns out that beta bar is the ideal value, but alpha bar is 10.5, but we used the ideal value 11.5 here in the formula for R. Gives me R equals 24.2. If you don't do that, if I were to use 10.5 in here instead of 11.5, you'll find that when you calculate the forces, you won't get balancing. You won't get the forces to add up to 0, add up to the horizontal and vertical components of the brace. Anyway, just plugging into the basic formulas, the vertical component of force between the gusset and the beam is 25.4. The shear between the gusset and the beam is 35.6. You have to remember what all these definitions were. I don't have the time to go through the whole thing again. M sub B, the moment that exists on the horizontal edge, and here you see the V sub B and the H sub B, is V sub B times the difference between alpha and alpha bar, which is 1 inch, which gives me a couple of 25.4 kip inches. And V sub C, vertical component over here, gusset to column, is 26.3. And H sub C, horizontal component between the gusset and the column, is 18.8. There's a note here that H sub C would be 0 for connections to a column web, except for special case 4. Why is that? Because for column web, E sub C would be 0, and so therefore H sub C would be 0, except for this special case. And M sub C, in this case, there could be a couple on this edge. If alpha, if beta, and beta bar were not the same, we would have a couple on this edge, just like we do here, and we would calculate that couple by taking H sub C times the difference between beta and beta bar, just like we're doing up here with V sub B and alpha bar. This is the normal component to this surface. H sub C is the normal component to this surface. So it would be H sub C times the quantity beta minus beta bar if, in fact, beta wasn't equal to beta bar. So I could have couples on both edges. And actually, in the manual, part 13, there's a discussion of this, of a way maybe to distribute them between two edges, if you want to do it that way, using some Lagrange multipliers. Okay. The next part of the connection that we'll do is the gusset to the column. And we have all the forces, we have everything we need, and we need to check all the limit states that are listed here, A, B, C, D, and E. We need to check the bolts. We need to check prying of the angles and the column flange. We need to check bolt bearing and tear out of the angles and the column flange. We need to check gross and net shear and block shear for the angles, and we need to check the angle weld. As you can see, there's a lot of work in these connections. Continuing, we'll look at the bolts here. Remember, the bolts had a bolt shear capacity, a design strength of 11.9, and there's 8 of them. So again, we have 95.2, greater than the vertical component that we're dealing with, gusset the column, 26.3. The thing that's different on this, though, is that we've got both shear and tension on these bolts, as we did last week in the prying action formulation, and that's why I did that. The most interesting case, really, is where you've got shear and tension. And you've got shear and tension on these bolts, you've got shear and tension on these bolts. So what's the shear per bolt? Called V sub bolt here is the total shear divided by the number of bolts. It's 3.29. What's the total tension per bolt? The required strength in tension per bolt is H sub C, the total tension divided by the number of bolts, 2.35. And the area of a bolt, 3/4 diameter bolt, is 442. Therefore, the shear stress per bolt that we need for the interaction equation is little f sub RV, is the shear per bolt divided by the area of the bolt, which gives me 7.44 KSI. Then the next slide will show the interaction equation, which you saw the last time in some detail. 1.3 times FNT minus, well, we had it in LRFD terms the last time, but here we have omega times FNT multiplied by little f times little f sub RV divided by FNB, but all of that can't exceed F and T. And what are these values? Table J3-2 for Group A bolts, which is what they're called now in the latest spec. That's A325 bolts. The tensile strength is 90. The last time I asked you might ask yourself, why isn't it 120? That's what ASTM says it is, right? Well, I'm leaving that as a homework problem for you. Go to the bolt guide and you'll find out. And F sub NV is 54. The shear strength, threads included, that's the numbers that you see in here, 54, 90. If you calculate all of this, you come out with F prime NT equal to 92.2, which is greater than 90, which is impossible. We can't exceed 90, so we use 90. I mean, it's possible for it to exceed, but for design purposes, we can't use more than 90. All this really means is that the shear stress on the bolt is so small that really it doesn't affect the tensile strength interaction-wise. So what's the reduced tensile strength of the bolt? It's F prime sub NT times the area of the bolt divided by the safety factor. That reduced tensile strength wasn't reduced at all. It was 90. So we're right back to the 19.9 that we had before. Greater than 2.35, we're okay for the bolt. So the next set of slides has got to do with prying. I think I said whenever the lead-in for the limit state is shown in yellow here, it's one that I am not going to go through in detail again because we've done it either here or we've done it in a previous session. And so we are going to skip, as it says down here in the bottom right-hand corner, to slide 75. Between 65 and 74, you've got all the calculations you need to check that yourself. There's a lot of homework to be done here if you really want to go through this stuff. Do you care? Well, I hope so. I mean, somebody's got to do these calcs. If you think you can come up with a better way to do it, then I'd like to know about it. But it's very tedious. There's no question about it. Now, this is prying on the column side, which we didn't do last week because we didn't have a column. All we did was talk about the double angle side, but I did say that you need to look at both sides. So here we're looking at the other side. Now, the column is continuous. So it would really be very, very conservative to say that the tributary length per bolt, the P here, is the spacing of 3 inches because I've got all this extra yield line that I can develop. So this is just a way to come up with an effective P, tributary length per bolt. This comes from this book, Handbook of Steel Connection Design and Detail, 2nd edition. The formula is given there. It was originally developed over here by Mann and Morris way back in the 70s, published in the ASCE Journal of the Structural Division in March of 1979. Note that we have an A bar and a B bar. A bar is the distance from the center of the hole to the toe of the flange of the column. B bar is from the center of the hole to the face of the web of the column. So continuing with all of this, we can calculate this P effective. We know what B bar and A bar is from the geometry. B bar is the gauge of the bolts minus the column web thickness divided by 2. A bar is the column flange width. Subtracting the gauge, divide that by 2. Using that information on the number of rows of bolts, which was 4, we can calculate an effective tributary length of 5.88 inches. If we were at the top of a column, then you wouldn't have all this up here, and the default option there, I think, is to just use 3 inch, use P effective here as 3 inches if you're at the top of a column. That way, we would be at least conservative and maybe not that conservative because we can't go above the column to get the yield line. So, again, the required strength per bolt, tensile strength per bolt, is 18.8 total divided by the number of bolts, 2.35. The gauge, the B dimension, is 5.5 over 2. This is minus half of the column flange thickness divided by 2. Gives me 2.56. B prime is the usual. Well, 2.56, 2.55, half a bolt diameter gives me 2.18. And A is a little bit different. This, really what we've got here is A bar. That's the width of the column flange minus the gauge over 2. And that came out to be, I've forgotten what it is, but it's a pretty big number. And A from the angles, for the other side, would have been 1.44. So you have to use the smaller of the two, because what's happening here is that the column flange is way out here someplace, The A for that is way out here someplace. But you can't have any prying out there. You have to have prying where at the smaller A. Right at this point is where the little Q force is going to work. So A prime is the same A that we would have for the angles, 1.44 plus half a bolt diameter. This is just the check that A can't exceed 1 1/4 times B. So we get A prime and B prime, and we get rho, which is the ratio, 1.20. Maybe I'm going a little bit too fast on this, but you've got all these slides in front of you. We've done this all before. The thing that's different here is that we're looking at the A bar from the column, and we're comparing it to the A from the angles. So we have all the dimensions that we need now to continue with prying action. P equals P effective, 5.88. Delta is 1 minus the size of the diameter of the hole divided by P, which is 13/16 over 0.588. Subtract that from 1. T sub C, in ASD terms, we have an omega in the numerator instead of a phi in the denominator, but everything else is the same. 4 times B prime times P times F sub U. Everything looks the same, but of course the B here is in ASD terms rather than LRFD terms, which was the 19.9. But the T sub C here will be exactly the same number whether you do this in LRFD or ASD. It'll be 8.71. This says greater than the thickness of the flange. Yeah, that's true, but that really doesn't mean anything. All we know is that as long as we got this value, 8.871, we could develop the strength of the bolt. We could develop 19.9. We don't have 19.9. We've only got 2.35. So continuing, alpha prime, we know exactly what that is. It comes out to be between 0 and 1 in this case. 0.565 is greater than 0, less than 1. So we would use manual equation 933, which is basically this equation here. T over T sub C squared, 1 minus delta alpha prime, gives me a Q, capital Q, of 0.717. T available is simply the bolt available tensile strength multiplied by this Q factor. 19.9 times 0.717 gives me 14.3, greater than 2.35. We are okay. Okay, next here is gusset to column bolt bearing. Again, the heading here for this particular limit state is highlighted in yellow, which means that we have considered this before. And we will not consider it again, but all the slides that you need to do it yourselves are presented here, and we will go to slide 87. So slide 87, we're still in the gusset to column connection. We haven't checked angle gross shear. That's what's shown here by this red line. What's the gross shear of the angle? Well, it's the length of the angle. 11.5 inches is the depth of the angle, the length of the angle, times the thickness of the angle, which was 3/8 of an inch, times the shear yield strength of the angle, 0.6 times 36, divided by the safety factor, 1.5 for shear yielding. There should be a 2 in the numerator of this equation, of this expression, because there are two angles. There's one near side, one far side. That 2 is actually included in the calculated value of 124, greater than 26.3. We're okay. We need to check angle net shear. That is kind of shown in here by the red. It's basically the depth of the angle, which is 11.5. Take out the holes. The holes are 13/16 plus a 16th, 7/8. So we got 4 times 7/8. Take that from 11.5 and we get 8. That's the length, the effective length. The effective length is 8 multiplied by the thickness of the angle, which is 0.375, 2 angles. The shear fracture strength, or the shear rupture strength, is 60% of the tensile rupture strength. Factor of safety in this case is 2. Gives me 104 greater than 26.3. Okay. Again, here we are with block shear in the angles. We have already done that. You see this formula here from section J 4.3. We've already done this. Earlier tonight, we've done it, I think, maybe in a previous. No, I don't think we have, but we've done it tonight. So we will skip that here. All the calcs that you need are given in the slides between here and 94, but we'll skip to slide 94. I hope you're not being disconcerted by this, but we are trying to get through the whole thing, and we will not make it if we have to do every one of these limit states. This is very, very time-consuming stuff. And that's why most times when you see this stuff presented, people just kind of say, yeah, we're going to treat block shear, and here's the answer. But if you really go through it, which these slides do, these slides treat every limit state that you have to consider in complete detail. But there's not enough time in an hour and a half to go through every one of them in detail. So we're going to look at block shear in the gusset. And the reason we're going to do that is for two things. We're looking at block shear here where there are no holes, and we're looking at two block shears. There's a block shear for shear, and there's a block shear for the axial force here. This is the basic equation that we have here. We're going to be looking at this red section that you see here. The first thing that we're going to check is block shear for shear. Maybe that sounds like a tautology there, but we've got a vertical component on this particular connection, which is V sub C. And we need to make sure that the gusset, this piece of the gusset, doesn't tear out on us. So for the shear check, this is block shear of the gusset for shear. The gross shear length is this length that you see here, from the top of the angle all the way to the bottom of the gusset. That's 14¼ inches. And the gross tension length is K. That's the horizontal length of the weld right here. It's the length of the leg. It's the length of the leg minus the setback. And the nets are exactly the same as the gross because there are no holes. So calculating the areas, the gross shear area is 5.34, and the net shear area is 5.34 because there are no holes, and the net tensile area is 1.31. So calculating block shear for this, we have shear fracture times the net shear area, which is 185, and we have gross shear yielding. Again, since there's no holes, the net and the gross are the same, but these values are different because this is yielding rather than fracture, 115. And then we have down here tension fracture, which is on this surface right here. That's 58 times the tension net area, which is actually the tension gross area since there are no holes. That gives me about 76 plus 115 gives me 191. Divided by the safety factor gives me 96. So the second thing that we want to check then is for axial. Remember, we got an axial force on this as well, right? I've got an H sub C acting on here, horizontal force. Now, all of the areas are exactly the same as I just calculated. Since there are no holes, the gross and the net are the same. But now they're interchanged. The shear area, the shear length is 3.5, and the tension length is 14.25. So the gross shear area and the net shear area are both 1.31, which was the tension area before. And the net tension area is what was the gross shear area before. It's 5.34. 5.34. So calculating all these values again, this is shear fracture. This is shear fracture, 45. This is shear yield, 28. This is tension fracture, 310, plus the smaller of these two, which is 28, gives me 338, divided by the safety factor gives me 169. So we've got these two limit states occurring simultaneously on the same surfaces. So it might occur to you that perhaps interaction should be considered on this. And the design manual, in a few places, the worked out examples consider a square, some of the squares kind of interaction. As you see here, this is the required shear strength. This is the available shear strength. This is the required axial strength. This is the available axial strength. All these numbers we've just calculated, so take the ratios and square them and add them up, you get 0.09, which seems like, what are we bothering doing this for? But this limit state can be very critical, especially in seismic connections where you've got fairly high loads. But for this particular connection, the loads are pretty light. Okay, next is the weld size. We're going to calculate this weld size right here, which is pretty basic stuff. It's a C-shaped weld. We have manual tables in Part 8 that allow us to do that. We calculate the resultant force on the weld, which is the H sub C, and the V sub C gives me 32.3. The angle between the vertical here, which is the long leg of this weld, and the resultant is the arctangent of H sub C over H sub V, which is the angle, gives me 35.6 degrees. The length of the weld, L, the vertical length, is the length of the angle, 11.5. KL, which is the horizontal length of the weld, is the length of the angle in contact with the gusset. It's 3.5. So therefore, K is 3.5 over 11.5 is 0.304. Once I know that, once I know where I am with K, I can interpolate to get X. There's actually a simple formula that you can derive for X, which saves the interpolation. But interpolating in there, you'd get X equals 0.057. A is equal to, or AL, well, AL is equal to the eccentricity right here. The horizontal eccentricity, E sub X, is equal to AL. So A is equal to 4, which is the angle leg, minus XL divided by L. This is just shown as AL plus XL. It's actually 4, but don't take AL and get rid of the XLs here. It's 4 minus X times L gives me 0.29. So I'm down in here, I'm between 0.25 and 0.3, so I can interpolate in that square and come up with the C value of 2.96. This is from manual table 8-8, which you see here, with an angle of 30 degrees. Why 30 degrees? Because our angle actually was 35.6, and we can't interpolate in these tables according to the manual. You have to go to the next smaller angle. So calculating the required weld size, this coefficient C1 is something that's almost always 1. It's 1 for E70 electrodes. If you use some other electrodes, it's another number. But in the 30-odd years that I've been involved in this, I've never used anything but E70 electrodes. But if you have to, you got a table 8-3 to do that. Then the formula for D min is given here as the resultant force multiplied by the safety factor, divided by C, C1, and L. And there's 2 here is because there's 2 welds. There's one near side of the gusset, one far side of the gusset. So 32.3 is the resultant force. 2 here is the safety factor. This 2 here is the 2 because there are 2 welds. This is the C factor. This is the C1 factor. This is the length, 11.5, which gives me 0.949 16th, less than 4, so I'm okay. Remember, we specified a 1/4-inch fillet weld here. T-min, you can calculate T-min by all of this, which is basically setting the fracture strength of the weld equal to the shear fracture strength of the gusset, which you see right in here. That would give you 0.101. This should be the other way, right? This is just to see if you're awake. 101 is less than 3/8, you're okay. All of this is manual equation 9-3. T min is equal to 6.19 times the number of 16ths divided by the tensile strength of the material. If, in fact, the T min was greater than the thickness of the plate, you would have to prorate the strength by the ratio of the thickness of the plate to the T min required. So your quarter-inch fillet weld might not be good for a quarter-inch fillet weld if you had too thin a plate. All of this is spelled out in the manual on how to do it. All right, continuing. This is the next part of the design is the gusset to the beam. Will it ever end, right? We've done gusset to column. We've done brace to gusset. Now we're doing gusset to beam. We got one more after this yet to do. What do we have to do for this one? We got to check the weld size between the gusset and the beam. We have to check the gusset for shear and tension. At the weld line, we have to check beam web yielding because we have a normal force on this particular joint, and we need to check for local beam web crippling because there'll be a normal force, possibly a compression on that edge. All right, this is for the welds. This is just the nominal weld strength, 0.6 times 70 times the area of the weld. And this quantity in the brackets is the strength increase, which you've seen before. I don't know if you've seen it in this session, but I know you've seen it in the previous one that Tom Murray did. If the angle between the loading and the longitudinal axis of the weld is 0, then this factor is 1. But if the angle between the loading and the weld is 90, then this factor is 1.5. Those are the two extremes. One of the problems with this is that you can't just add these things together if you have the two of them in the same joint, which I know you've seen before. What you saw in the previous slide is more commonly shown as, in ASD terms, 0.928 times the strength increase factor times the number of 16ths times the length of the weld. And if this is the length of one weld, maybe you should have an N in here for the number of welds. LRFD 1.392. So let's check the weld. We have a shear component. This X here is the horizontal component of the kips per inch of weld. It's the shear on this edge, 35.6 divided by 20, 1.78 kips per inch. We have two vertical components, or normal components. This is due to the V sub V, 25.4 divided by 20 gives me 1.26 kips per inch. And then we have a bending component. And this is one of the reasons why this was included, just to illustrate. M sub B is 25.4 kip inches. The length of the weld is 20 squared. In the denominator times 4, this is the plastic section modulus, gives me another component of 0.254 kips per inch. So the peak stress would be the shear stress plus the maximum normal, which gives me 2.34. And then the average is, say, the shear plus the peak plus the shear plus the minimum, the difference between the two vertical components. Take the square roots of those, add them together, take a half of them. This 1.25 here is a ductility factor that comes originally from work done by Ralph Bridget about 25 years ago. It was 1.4 to start with, but Chris Hewitt, who was an AISC engineer for a while, just felt that that was overboard, a little bit overkill, and he and I wrote a paper, but he's the lead author. 1.25 was sort of the value that we achieved, that we came up with. This paper is 10 years old, 2004, AISC Engineering Journal. So what we're doing here is we're comparing the peak to 1.25 times the average, whichever is bigger. That's what we're going to use to size the weld. Now, somebody said in one of the questions, he had been told that if in fact you say special case 2 and you get a big M sub P on this, that you don't have to consider the ductility factor. Absolutely correct. If 1.2 times the average is less than the peak, you don't have to mess with it. In this particular case, the angle between the longitudinal axis of the weld and the resultant is 40.6 degrees. So therefore, the strength increase, that 1 plus the sine, 1 plus a half of the sine of 40.6 degrees to the 1.5 power is 1.26, all of this right here. So we have 0.928 times 1.26 is the strength of the weld. So looking at the peak and 1.25 times the average, you take the bigger of the two and divide it by 1.928 times 1.28 and 2 welds gives me 1.18 sixteenths, which again, going the wrong way here, is less than 4, so the 1/4 inch billet is okay. So correct your notes in that regard. It's obviously going the wrong way. Also, you should be checking, and we should have checked before, that this 1/4 inch fillet that we've got, it satisfies the AISC min, and it does. AISC minimum fillet weld for 3/8 plate or 3/8 angles is 1/4 of an inch. So, we need to check the gusset adjacent to the weld. This is basically checking the minimum thickness of the gusset for shear. This is the kips per inch of the gusset, and this is the shear yield strength of the gusset. Factor of safety 1.5 gives me 0.124 inches. This is kips per inch. This is KSI, so I get inches for the result of this. That's less than the 3/8. I'm okay. Tension, likewise, the sum of the vertical components, the normal components, was 1.27 plus 0.254. That's divided by the tension yield strength, which is 36 over the 1.67, which is about 21.6, gives me 0.071. Less than 3/8. We're okay there too. Then checking beam web yielding. What are we doing in here? We're coming up with an equivalent normal force, P equivalent. The moment divided by half the distance, half the length of the weld gives rise to the couple forces that act at the half length of the weld. So I get some force, M sub B over the length of the weld over 2. And what I'm doing is doubling that force so that I've got one up and one down. I'm putting them both up, calling that an equivalent normal force, and I add to it the V sub B, gives me 30.5 kips for the full length of the weld. You could do this for half of the length of the weld. There's other ways to do it, but I think this is probably the most convenient. I think it's a little on the conservative side, but usually it's not an issue for most problems. So that is the required strength. What is the available strength? This is from the AISC spec, the contact length plus 2.5 times K, multiplied by the yield strength, multiplied by the thickness of the web, divided by the safety factor, gives me 327 kips, greater than 30.5. You might say, well, hell for good, but there are many cases, especially in seismic problems, where the forces acting on this interface are really, really high, and so you can't say this is a throwaway limit state. The last one is web crippling. This is from the spec for web crippling. It's a complicated formula that we have here. I'm not going to go through it in detail, but substituting all the numbers into it, you've got all the numbers. There's an extraneous 2 in here. This 2 shouldn't be there, so cross that one out, but this 311 is the right number. Greater than 30.5 kips, okay. So where are we now? We're all the way up to the beam to column connection. We're looking at this one. And on this one we've got F limit states to look at here. We've got to check the bolts, we've got to check prying of the angles in the column flanges, we've got to check bolt bearing and tear out, we've got to check gross and net section shear, block shear for the angles, block shear for the beam, and the angle welds. We've checked all of those before. Well, we've got a discussion here. We need to do one thing that we haven't done before. We need to introduce the gravity shear, which we haven't talked about before, but this is a beam. It's probably got gravity loads on it. In this particular example, we're using half of UDL, which is about 41.9 kips. You've also got some other things. This is a complicated connection. There's lots of different things that you might have to consider. They're not going to be considered all here tonight, but what we've got is a vertical force of 24.5. We've got no transfer force specified. We've got a gravity shear, 50% of UDL. The UDL from this table, 3-6, comes right from here. This is the total uniform load. Take half of it, put it on either end. That's where the 41.9 comes from. We could have, for the vertical component, we could have the gravity shear plus vis-a-vis for the top, which is 0 in this case, plus vis-a-vis for the bottom, which is 25.4, gives you 67.3. You should check the beam for this. The beam will be good for that, 67.3. And then for the H, what are we going to do for H? Well, we could have the max of H sub C for the bottom, which is really all we've got in this case. We could have an H sub C for the top. We could have a transfer force. There's various ways to consider this, but in our particular case, it's 18.8. But there are some considerations here that are worth thinking about. If you consider distortional forces will always reduce the H sub C that we have in here, these H sub C's top and bottom. They'll always reduce those. But we're not considering those. So we could use H equals H sub C, that's the horizontal component from the bottom, and we could subtract from it what's on the top, plus the transfer force if we're checking an exact load case. We could add the opposite H sub C if the braces are both in compression, which sometimes happens. Conservatively, the maximum V will be checked with H, but really, if we have a bottom brace like this and the brace is in compression, it's going to be pushing up. It's going to be reducing the shear in here. There's all kinds of things that you need to look at for this connection, and there's no way that I can consider all of them right here. You need to look at exactly what you're dealing with. This slide tries to point out that perhaps you could, if the exact load case is not known, you could take the maximum of H sub C for the bottom, or the sum of H sub C top plus P sub C. So kind of saying take this plus this or that. Or if the exact load case is known, maybe take what's on the bottom, this, and subtract from it the sum of these two. That's a possibility. But anyway, in our particular case, we have a simple case where we just have 18.8 kips here. Sometimes, because of what's called column shedding, it could be that you have a small lateral force here, but you got a really high gravity load in this column, and the column will shed load to the brace, in which case you could have both braces in compression. Anyway, there's all kinds of things that you need to consider here. The beam to column bolts, this is one of the many limit states. All of them will be listed here in your slides between here and 159, but we are not going to do them tonight. They're all in your handout, so you can do every one of them yourselves. So let's skip to 159. At 159, the only thing here is block shear again, but we've got block shear now for tension, for an axial force on this thing. All of these parameters in here are exactly what we did before, but a piece of the beam that you see here, if the horizontal force H sub C or the transfer force or all that stuff we just talked about gives a tension on this, you could tear out that piece. And so you need to consider that. You need to consider block shear for axial. And since there are no holes, we've already gone through this, the net, the lengths for gross and net are exactly the same. Note that we're saying here that block shear is checked for axial load only. Block shear is not checked for the vertical components here because the beam isn't coped. In order for this to fail in block shear, you need to rip out the top flange, and we don't have a limit state for that yet. Perhaps there should be one, but whatever it is, it's not block shear. So right now, in all of the AISC publications, block shear is not coped if the beam, block shear is not checked if the beam is not coped. anyway, going through this, which we've done before, you calculate the areas that we have here, and you can calculate then the block shear strength, just like we've done before. This is shear fracture. This is shear yielding. We take the smaller of the two and we add to it. Tension fracture, which is 321 plus 90 gives me 412, gives me 206 when I have it by the factor of safety. And then the rest of this, I believe we've done all of these before. And so we'll skip to slide 168. And 168, really, we're finished. You've got all of the limit states that you need to consider for all four parts of this connection. We've done at least one of them in every situation here. Now we're just saying, if either the gusset to column connection or the beam to column connection cannot be made to work, if you've got a problem, economically maybe, it may be necessary to change the force distribution. Perhaps you want to use a delta vis-a-vis, which was special case 2. That's a possibility. Or maybe you want to change the dimensions of the gusset, make it bigger. The gusset that we picked is pretty compact. It could be made bigger to eliminate problems. We're saying here for economic connections, and I think you saw this in the first or second session, use the uniform force method. Certainly there are other methods out there that you can use, but I don't think you'll come up with a more economic design if you do that, and I don't think you'll get one that's closer to what I can call, quote unquote, the true solution, the one that satisfies equilibrium, limit states, and compatibility. Use decent-sized columns. Don't use really, really tiny beams when you have bracing connections. When you do your computer analysis, the beam might not even know that there's any force coming to it by the brace because the brace connects basically to a node. So you end up maybe with a 10 by 12 or something like that with a brace that's got 400 kips in it. There's no way you're going to make that work, not without doublers, haunches, and everything else. So consider the fact that if you got a brace with a significant load in it, that you ought to have a fairly decent beam. And use the same depth beams on either side of the column to avoid any eccentricities relative to transfer forces. Consider net section capacity when picking your braces. And then the last thing, which almost is never done, provide the actual loads if you can. Maybe give the connection designer a series of load cases so that he can or she can pick the ones that control rather than using envelope loads. For summary, we've basically talked about all this. We've done a corner connection here. This is sort of non-seismic, the kind of ordinary design without any special detailing requirements. We'll see a lot of detailing requirements next week. We began the example with the brace to gusset connection because we need to do that first to size the gusset. The gusset dimensions were determined based on the brace to gusset connection. The gusset to column connection, including prying action, was checked, followed by the gusset to beam connection, finally the beam to column connection. The beam column connection is the worst of the lot because you've got top and bottom braces possibly, transfer forces, distortional forces, all of these things, column shedding. I mean, there's all kinds of things that you might have to consider in that. And with that, my time is about up, and I thank you for your attention.
All right. Thank you, Bill. Thanks for getting through that example. We do have several questions. Sorry, go ahead.
I said, yes, it's tedious to go through these things in detail. Anybody that does these for a living has some kind of software that can do at least the simpler ones, like the one I did here tonight. Go ahead, Brent.
Okay. Well, there might be a good transition into a couple questions I got on production of these design of these connections. So one question is, would you care to share or estimate how many engineering hours would typically be spent on one connection such as this? And then I guess further beyond that is what what aids such as tables, spreadsheets, software would you use to increase productivity, and what is the effect typically?
Well, I would say that if you were going to do these professionally, you need to do a spreadsheet, or you need to write yourself a hard-coded program of some sort. It's pretty basic stuff. This particular connection that I did here tonight, we have in-house software at Surveys that could do every aspect of that connection. The biggest part of it is inputting the data, which would probably take about 10 minutes, and then AutoCADing a picture. We don't have software that produces pictures based on the calcs. We haven't gotten that far yet. So it might be to do just one of these. I would say maybe an hour, maybe 20 minutes, depending upon whether or not we can use connection pictures from other jobs. But the calculations themselves are done very quickly. I don't know that there's any software out there that can do this. There may be. I think maybe Tekla's got some. I think maybe, what is it? There's one on the West Coast. I can't remember the name of it, that sells a software program that does bracing connections. SDS2 can do some of this. It's very tedious to do this. I mean, if you do more than a couple, you're going to say, wait a minute, I need to have somebody sit down and do a program for me so that all I need to do is put in the data. And that's what we do. I would say probably one connection like I did tonight, total engineering hours from getting the loads, once we have the information, to getting what we call a design sheet, a P sheet, would probably be an hour or so. And it's not going to be done in 10 minutes because you need to draw pictures, you need to check it, you need to do all that stuff. There's a lot of work, even if you have software.
Okay. All right. We've got a handful of questions regarding the Whitmore section. So I'm going to go to slide 47. Do you see that there, Bill?
Yep, I see slide 47.
Okay, first question is, what happens when the Whitmore section goes into the beam? How is that handled?
Well, generally, I referenced a paper by Carlo Lini and myself, Modern Steel Construction. I think it was 2012. That answers that question. That goes into basically. If it doesn't make the Whitmore section too unsymmetric, I would include the part that goes into the beam. You don't see that here, but if the Whitmore section were a lot closer, say into the joint between the beam and the column, it's possible. And if the brace were more shallow, if it were a shallower angle, you can see that the upper tip there would very likely intersect the web of the beam. Now, if the gusset is 836 and the beam is grade 50, which it always will be, the material is stronger. I would use the full Whitmore section, maybe even prorate the strength up a little bit. But I would be careful not to make it too unsymmetric. I wouldn't want to see a lot of it on one side and nothing on the other side. The Whitmore will be essentially symmetric if part of it goes into the beam. But it could be, the thickness of the web is less than the gusset. Maybe you want to consider that. Look, all I can say is all of these questions were raised by other people, and they were put together in this article in Modern Steel Construction. And maybe you could maybe post a reference to that so that everybody can take a look at it if they're interested. Okay, go ahead.
We can follow up with a link to that. I believe the reference is in the July 2011 MSc. That's July 2011.
Well, then I'm off a year, huh? All right, 2011 instead of 2012. I said 2012 at least 2 or 3 times here.
Okay.
You can download that, I believe. I don't know if you can do it for free, but I know it's online. You can download it if you're a member anyway.
Yeah, there's free access to the online version of Modern Steel. Okay, next question. Can you account for the strength of the weld for the gusset plate to beam that falls outside of the Whitmore section?
I would say yes. That question has come up in a few different places. But the Whitmore section, if the Whitmore section is really, really close to the gusset to beam intersection, maybe there's some validity to that, but I don't see why I can't cut a horizontal section through there and say that section is effective. I always use the full L sub W, L weld in this 47, slide 47. I don't know, maybe, I don't think there's any research that shows anywhere that you can't do that. The Whitmore section itself, you know, the 30-degree angle is just sort of a maximum. There's research that's been done in Canada that says maybe you should use 45. There's other calculations that are done using a smaller angle to make the gusset more compact, because when you have the 2T yield line and seismic connections, the Whitmore section basically pushes makes the gusset a lot bigger. So I would say I feel comfortable accounting for the part of the gusset beyond the Whitmore section in this slide 47. Let's say to the right of the top edge of the Whitmore section and the right edge of the gusset.
Okay. So I'm just going to move up one slide to slide 48, where you discuss determining your K value for the gusset. And the question is, if your gusset is not connected to both the beam and the column, how would that affect your K value?
Well, let us say that in this particular case that we connected the gusset only to the beam and not to the column, I would say that I would use a K of 1.2 in that case. In other words, I'm assuming that I could get a side sway mode. So I would use 1.2 if I was connected only to one edge.
Okay. A question regarding the gusset. Do we need to check the gusset for bending?
Because of the eccentricity in this case? Is that what the question is addressing?
I apologize, Bill. I don't know for sure. Maybe I can get a response on that one.
Well, there was a... I'm sorry.
No, go ahead.
There was a question on session 3 about that. Would I consider bending on the gusset due to the fact that the gravity axis of the WT is way above the gusset? You know, wow, 1.13 inches. Would I consider that? And I said no, because that's considered in the design of the brace. So I would not consider that, if that's what we're talking about, out of plane bending out of the plane of the slide that you see here because of the lap eccentricity, for instance, and the eccentricity of the WT itself.
Okay.
If you're going to have this WT in compression, that WT should be designed for that eccentricity. Either that, or this needs to be a different connection than what we're using here. There's a discussion of this in the commentary of the 14th edition specification. I don't know what section it is, but if you go to that, you'll see the different cases that need to be considered.
Okay, I'm going to move forward to slide 96. This is looking at checking block shear of the gusset.
Yep.
So the question is how do you have block shear with tension in the brace as is shown? It seems that V sub C is upward to the beam.
It would be, but remember that the brace can be plus or minus. The 75 can be plus or minus, so the brace could actually be pushing up, and the gusset to column connection could be pushing down instead of up. So unless I know that the brace force, P sub A here, is always plus 75, if it were always plus 75, then I wouldn't have to check this limit state. But I'd say 9 times out of 10, or 99 times out of 100, we're given that the connection designer is given a plus or minus, or plus something and minus something. So I always check the worst case. There was this was addressed on the slides to some extent, that if, for instance, the brace is in compression, the V sub B between the gusset and the beam is pushing up, which is actually resisting the V sub G, the gravity shear. So you could look at the difference between the two. But what if the brace changes and goes in tension? Well, then you got to add the two. And so just so we're not doing a whole bunch of different cases here, you could see that it would take enough time to do just one. And there's all kinds of possibilities of missing something. Generally, the connection designer takes the worst case and runs with it. And the worst case in this case is to consider the block shear limit state that you see here.
Okay, I'm going to go to slide 112. The question is this one half fraction that's in the equation. Does the 1/2 factor account for welds on both sides?
No. What we're calculating here in the square brackets in that particular formula is an estimated maximum shear stress peak, like you see up here, the shear plus the maximum normal, and then the shear plus the minimum normal, which would be the direct normal and the bending normal, which could be the same, could be 0. We're just taking those two and adding them together, and then taking the average, dividing it by 2. So the 1/2 is just calculating the average of the two inside the square bracket.
Okay. Next question regarding the bolted portions of the connection. Is bolt slip taken into account in the bolt shear capacity?
No, these were bearing type bolts and standard hole. There's no specific consideration of bolt slip. The bolts are basically assumed to have slipped into bearing.
Okay. All right. Well, we've got a couple more questions, but we are really about out of time here. For those of you that we did not get your question, we'll for sure follow up and get you an answer within the next week. So, thank you again, Bill, and thank you all for your attendance and for your questions this evening. It was a good session, and we look forward to you join us again next Monday.